Hey, it's good to be here. It's great to see all these presentations explaining some of these really cool big vulnerabilities. And I'm really excited to close out the day with just some of the vulnerabilities that have been disclosed through our platform and paid out millions of dollars. So Jay talked a lot about incentives when you find vulnerabilities. What do you do when you found this bug in a project's code that could have resulted in hundreds of millions to billions of dollars in stolen value? There are some hard questions that come up, like how can you reach out to a vulnerable project, who to trust to disclose the issue to, should you exploit it yourself, let alone launder hundreds of millions of dollars? What Immunefi is trying to do is hopefully make that an easier decision for white hats, gray hats, and even black hats out there who are faced with a situation like this. And that decision should be to responsibly disclose issues to projects so they can safely mitigate these vulnerabilities and protect users in the ecosystem from real-world damage. So who am I? I'm Alejandro Munoz-McDonald. I'm a smart contract engineer and triager at Immunefi. My background is in computer science. I was a software developer before joining Immunefi, but I got my start in Ethereum security in 2017. I really dived into bug bounties and security in 2020. I actually started submitting bugs to Immunefi before I worked for them. In my free time, I'm a white hat. I've directly saved over $15,000 in tokens with flashbots. I've helped a friend who got spearphished saved his NFTs when his private key was compromised. And I've also created educational content related to security in the space. We recently put out a YouTube video on one of the bugs I'll be covering in this talk. And my Twitter is unsafecall. So what is Immunefi? If you don't already know, we are the largest bug bounty platform in crypto right now. We have a website where white hats can safely and securely submit their bug reports directly to projects. We also work closely with projects to help them understand the importance of high-value bounty rewards when a project has millions of dollars of value locked within them. We have over 40 million in bounties paid out to white hats, 145 million in bounties available right now, and 20 billion in hack damage averted. So what does Immunefi do for the community? We're always creating educational content to onboard more white hats into the ecosystem. We write postmortems with permission of white hats and projects and post them on Medium. We host hacker hangouts on Discord. We started the YouTube series, which explains vulnerabilities and how to create proof of concepts for them. So yeah, we're really big on that. So now we can take a look at just some of the bugs that have been paid out millions of dollars. Yes, that's millions for a single bug. For those of you with Web 2 bug bounty experience, payouts that large are just like unheard of. But we believe they're necessary to incentivize security in a space where bugs, have massive direct impact to honestly ridiculous amounts of funds. So let's get right into it. Cool, so the first vulnerability I'm gonna review is the Polygon Double-Spend. Gerard Ragnar submit a critical vulnerability on October 5th of 2021 that affected the Polygon Plasma Bridge. This could have resulted in the theft of $850 million of funds. So the Plasma Bridge, a bridge is basically a set of contracts that help move assets from the root chain to a child chain. The Plasma Bridge helps bridge assets from Ethereum to Polygon. So a really quick overview on the Polygon Plasma Bridge. A user deposits tokens to the Polygon contract on the root chain, which is Ethereum. The token deposit transaction is confirmed on Ethereum, and the corresponding tokens will be minted on the Polygon chain. Those tokens are ready to be used on the Polygon network. And then when a user is ready to withdraw from the child chain, Polygon, they can do so by initiating the withdrawal from Polygon. So that's like a checkpoint interval needs to be passed where all blocks have been validated. And then the checkpoint is then submit to the root chain contract. An exit NFT token is minted of the value the user wants to withdraw, and then another waiting period is initialized. The user needs to wait 7 days before being able to withdraw their funds. After those 7 days, you use the process exit procedure, and the user can claim back those funds to their Ethereum account. So the disclosed bug had to do with that withdrawal step there. So The withdrawal process, that is getting tokens from the child chain back to the root chain, starts with burning the representation tokens on the child chain. So after that burn is confirmed, a user can call start exit with burnt tokens function on the ERC20 predicate contract on the source chain. So that's where the initial checkpoint is timestamped for the 7-day waiting period. And what are the parameters that need to be passed in? Well, it's the exit payload. The exit payload contains all information about the funds that are being transferred from L2 to L1. And then you proceed with the exit. So the burn transaction needs to be a successful and valid one. That exit can only be called after that checkpoint is included in the root chain alongside the burn transaction. And then a user should call the function and submit the burn proof. So the main vulnerability lied in how Polygon's withdraw manager verifies the inclusion and uniqueness of the burn transaction that happened. So the goal of the function on the left there, as the name suggests, sorry if it's small, we do have postmortems about all of these vulnerabilities on Medium, and you can review these images there. But the main idea here is, for the function here, is to verify the inclusion of the burn transaction receipt during that checkpoint. A crucial parameter during the exit proof is something that's contained within the Merkle proof, which is the branch mask. Why is this important? Well, there's an exit ID value used in the verification of uniqueness of the burn transaction, and that branch mask is used to generate that exit ID. The invariant that should hold true here is that an exiting transaction only ever has one exit ID. So the branch mask is HP encoded and then later on decoded in the Merkle Patricia proof verify function. And because of the implementation of the decoding into an array of nibbles on the right there, it actually ignores some of that value, and the differences in those areas don't cause the decoding to be rejected. So the same value as decoded by the Merkle Patricia proof may have multiple encodings as the uint256 value. This is really bad because that value, the uint256 value that's being decoded is used to avoid replays. So the same proof with a slight modification could be replayed due to the issue of ignoring some of its content when decoding for the proof, but using the entire value during the replay protection. So what does a step-by-step exploit look like in this case? Well, you just deposit a large amount of ETH tokens to the Polygon through the Plasma bridge. After confirmation of the funds being available in Polygon, you start the withdrawal process. You wait the 7 days, and then you resubmit the exit payload, but with a modified first byte of the branch mask. So that same valid transaction could be resubmit up to 223 times. So you have like a 200x hack here, and you just profit. So as it turns out, the first byte of the encoded branch's mask is actually always supposed to be 0. The fix was just to check if the first byte of the encoded branch is 0 and not just to disregard it. The next vulnerability I'm going to talk about is the Polygon lack of balance check. I swear I'm not picking on Polygon here. White Hat Leon Spacewalker reported a critical vulnerability to Polygon on December 3rd, 2021. Over 9 billion Matic was at risk. A Black Hat or set of Black Hats have already managed to steal 800,000 Matic tokens using the same exploit. But there was a second White Hat that reported the bug to Polygon and also received 500,000 Matic. So the vulnerability here was a lack of balance allowance check in the transfer function. Real quick, the Matic token is the main token of Polygon ecosystem. So it's like Ether, but for the Polygon network. The most interesting thing about the Matic token standard is it's the native gas paying asset of the Polygon network, but it's also a contract deployed on Polygon. So this contract is the MRC20 contract. Having the network token be a contract on the chain itself allows for the possibility of transferring Matic tokens like gaslessly with the transfer with SIG function, which is something you can't do with Ethereum. But transfer with SIG, how does that work? So looking at transfer with SIG, the user who owns the tokens signs a bundle of parameters, which includes the operator, the amount, the nonce, and the expiration, and that signature can be later passed to the MRC20 contract by an operator to perform the transfer on the behalf of a token owner. Yeah, it's free for the token owner, but the operator forwarding the signature does still pay gas. In the transfer with sig function, though, we first verify that the signing hash has not already been used. So this is preventing replay attacks like we just saw. After that hash is verified, though, we extract the token's owner's address using EC recovery and pass that into the transfer from function. EC recovery takes that data hash and the signature. Smart contracts on Ethereum have access to built-in EC DSA signature verification algorithm through EC recover. So this is a built-in function that lets you verify the integrity of a signature over the hashed data and returns the signer's public key. This EC recovery function is a wrapper on top of the standard EC recover that lets you pass a packed signature without needing to separate the V, R, and S. So what's the vulnerability here? Well, to exploit this vulnerability, we don't need to do anything too complex, thanks to how the EC recovery function was implemented. We can just call transfer with sig function without a valid signature, and thanks to the lack of a check to see if the EC recovery wrapper function returns the 0 address, we can exploit a vulnerability here. So EC recover returns the 0 address when an address can't be recovered from a signature. You can see in the bottom right there in the code all the way at the bottom, there's a require statement that checks if the returned address is 0. It should revert. However, at the very beginning of the function, the signature length is checked to make sure it's exactly 65 bytes long. And if it isn't, it doesn't revert. It just returns the 0 address. So there's a second path which could return 0. The 0 address will then be passed into transfer from, and it's very common to projects to send tokens to the 0 address to burn them, so this bug would have allowed the theft of funds which were assumed to be lost forever. But it gets better. It gets better than this. The issue with the EC recovery function wasn't even the main issue. The main issue here is that the transfer from will call the transfer function directly without even checking whether the from has enough balance. So the function that takes the balances, the function transfer from takes the balances of the from and to address and just passes them to the transfer, which also has the same issue. It doesn't check that the sender has enough balance. So the bug in the token could have allowed an attacker to essentially mint an arbitrary number of tokens from the MRC20 contract. So yeah, that means all 9 billion in Matic could have been stolen. And I think Matic was like $2 at the time. So yeah, this is a 2.2 million bounty payout from a bug like this. Next bug, phantom functions. So DDoB disclosed a major vulnerability to multi-chain on January 10th of 2022. Multi-chain is a cross-chain router protocol. Basically another bridge. Bridges usually have very high TVL since tokens are being locked on the source chain side until the synthetic tokens on the destination chain are burned. This vulnerability would have affected $431 million of WETH on Ethereum alone, 367 million for the bridge contracts, and 40 million from other networks. So this bug is essentially a $1 billion bug. Multi-chain actually made a public announcement to revoke approvals for the contracts. It was that bad. So the attack vector here was actually pretty novel. The Solidity and EVM developer security community should definitely be aware of this type of issue. And just as a side note, there are actually 2 separate major vulnerabilities here, one involving WETH and a vault contract, and the other one involving the router contract. I'm just reviewing the ERC20 vault contract issue. So what was the vulnerability here? So this one was in multi-chain's AnySwap v5 ERC20 contract. A little bit of context. Smart contracts in Solidity can contain a fallback function. This code is called anytime a function is invoked on the contract, but the contract doesn't implement a function with that signature. If you make it payable, it's also called whenever your contract receives the native token Ether. In newer versions of Solidity, there's a separate receive function for when Ether is sent with no call data, but with WETH in the top left there, it implements a default payable function to have some logic that allows people to send Ether directly to the contract and then get the wrapped Ether tokens in return. So back to the AnySwap v5 ERC20 contract. The contract exposes a way to deposit funds and have them attributed to your account. The use of transfer from there on line 3 in the bottom image relies on an approval of the AnySwap contract before making the call to deposit. So the use of message sender in the function means the contract can only transfer your tokens if you've made an approval and are the initiator of the call to deposit. So that means you have to make 2 separate transactions, the approval and the deposit. However, there's a second path to deposit funds. Deposit with permit allows depositing of funds by a relayer. So this means the user depositing funds doesn't need to be the account to call deposit with permit, and the approval and transfer can occur in one transaction. Permit was introduced in EIP 2612, and it extends the ERC20 token standard and allows users to modify the allowance mapping using the account derived from an off-chain signed message instead of through message sender. This essentially improves user experience by allowing the approval, which is the signature, and the transfer to happen in a single transaction. We just lost the TV there. Can we get some help over here? We have a technical issue. Sweet, okay, back to where we were. Thank you guys. So what were we talking about? We were talking about permit. So permit was introduced in EIP 2612, and it extended the ERC20 token standard and allows users to modify that allowance mapping using the account derived from an off-chain signed message. Right, so the EIP defines a list of conditions that must be checked, like checking the deadline has not passed, ensuring the recovered address is not 0, validating the nonce, etc. Otherwise, the transaction should revert. An important check that occurs here is checking that the R, S, and V is a valid signature from the owner of a message. So just relying on a call to permit, contracts end up outsourcing the signature verifications to tokens they integrate. So, so let's take a look at the deposit with permit function at the bottom there. So permit is being relied on to perform an important security check, verifying that the signature is valid. This is where the $1 billion mistake was made. So not every ERC20 compatible token implements a permit function. So WETH does not define a permit function, but it does, however, define that default payable fallback function. So when deposit with permit calls permit on WETH in line 8, the fallback function on WETH is invoked, and since no other functions match the permit function signature, the fallback function is just invoked. The fallback function on WETH just calls WETH deposit. Message value is 0. There's no change to the balance. The call emits an event and just returns successfully. So literally none of the parameters being passed to the permit call are being checked. It's basically like the call to permit was never even there. Now you might think that's fine. The contract won't be able to then use safe transfer from to transfer the target's tokens since the call to permit did nothing and no new allowance was set. But if a target had made an approval to the AnySwap v5 ERC20 contract in the past, the contract will already have an allowance set and the safe transfer from will succeed. So all WETH and account approved the AnySwap v5 ERC20 contract to transfer can be stolen by a call to deposit with permit with any arbitrary values for the signature. So in the case of an infinite approval, this means like any WETH an account ever received in the future could also be stolen. So the takeaway here is that callers should not rely on permit reverting for arbitrary tokens. The call token.permit never reverts for tokens that don't implement permit and have a non-reverting fallback function like WETH. And DDoB has dubbed this phantom functions. So a contract with a phantom function does not really define the function, but accepts any call to it without reverting. Cool. So I've got one more bug for you guys. This is the Wormhole uninitialized proxy. So Satya disclosed a critical vulnerability in the Wormhole contract core bridge contract. This was actually not too long after their big hack where they lost around 300 mil. So I feel kind of bad for Wormhole, but it really shows these incentives are working. They set up a bug bounty program with us shortly after the hack, and that led to the responsible disclosure of this bug. So I don't have a number for funds at risk, but this was likely in the hundreds of millions. And the bug had to do with an uninitialized proxy. Some of you out there who already know about uninitialized proxies are like, what the hell, $10 million? That, you know, that could have been me. I'm here to say yes, it could have been you. That's why it's so important to get eyes of technical people like all of you looking at our bug bounty programs. So, you know, some of these projects are making, you know, simple mistakes that could lead to huge amounts of lost funds. But as long as we have a community that, you know, understands the importance of responsibly disclosing bugs by setting up the proper incentives where you can get rewarded for doing the right thing, we can help secure the longevity of the crypto ecosystem as a whole. Yeah, so that being said, uninitialized proxies. So in Ethereum, there are three major types of contract calls. There's a regular call, there's a static call, and there's a delegate call. When you do a static call, the expectation is no state is changed. And then when you do a regular call, when contract A on the left there makes a call to contract B by calling some function foo, the function execution relies on contract B storage, and the message sender is set to contract A. So changes made to state during that function call in contract B only affect the storage of contract B. However, when the same call is made using delegate call, the function foo would be called on the contract B, but the context is contract A. So this means the logic of contract B is being used, but any state changes that are occurring in function foo would actually affect contract A. So why would anyone want a delegate call? Well, delegate call makes it possible to create upgradable contracts using a proxy pattern. A proxy contract A redirects all the calls to implementation contract, whose address is stored within contract A storage. When an upgrade is needed, the implementation contract A points to can be modified. So you have two contracts, the proxy where the storage lives, and the implementation where the code/logic is. So there's two really common standards for proxies from OpenZeppelin. There's TPP, which is Transparent Proxy Pattern, and UUPS, Universal Upgradable Proxy Pattern. There are a few differences, but the major one is with TPP, upgrade logic is in the proxy itself. With UUPS, the upgrade logic is actually in the implementation. So in the standard, it's upgrade to and call. Calling upgrade to and call on the proxy delegates to the same function on the implementation. So it's basically like a pass-through. UUPS is slightly cheaper in that way. You know, you don't have to have checks in the implementation. In the proxy. So yeah, something to note, when UUPS proxy contracts are deployed, the constructor is instead an initialized function. So since we can't call the constructor code of the implementation contract, since it just doesn't exist after deployment, we have an initialized function. So this is defined in the implementation, which defines some initial parameters, owner. In many cases, developers use the upgradable versions of the standard OpenZeppelin contracts, which have the initialized function defined. So yeah, so in OpenZeppelin's UUPS implementation on the left there, the initialized function for the implementation calls ownable init. So the implementation extends the ownable contract, and you know, you get admin access if you are the initializer, essentially. So being an owner of a UUPS implementation contract means you can control the upgrade functions. So in particular, the owner of an implementation can call upgrade to and call directly on the implementation contract instead of going through the proxy. And apart from changing the implementation address to a new one, The function atomically executes any migration or initialization function using delegate call and the data passed to it. So since the upgrade logic is in the implementation, whoever calls initialize on that whoever calls initialize first on the implementation contract has the privilege to call this function. So what happens if the initialization function of the new implementation executes self-destruct? You know, the delegate caller will be destroyed. So we can cause the implementation contract to execute self-destruct in its own context through the delegate call in upgrade to and call. And since the upgrade logic for UUPS proxies is supposed to exist in the implementation, that proxy will never be able to upgrade the logic contract it points to, since no code now exists at the address that it was pointing to as its implementation. So what's the attack chain here? The attacker calls initialize on the implementation contract to become the owner. If nobody had called this function yet in the context of the implementation, the call works and makes the attacker the owner. And once you're an owner, the attacker can deploy a malicious contract with self-destruct. The attacker then calls upgrade to and call on the implementation contract as the owner and points to the malicious self-destruct contract. And during that upgrade to and call, the delegate call calls the initialization with self-destruct, and the implementation now just does not exist. So this proxy contract is pointing to nothing, and it is essentially useless. And this just leads to frozen funds. What you need to look out for is if your UUPS implementation has a delegate call available, you want to make sure to call the initializer on it, or just don't allow calls to be made directly on an implementation contract. So I think this is our biggest bounty payout to date, $10 million for one bug. And it's really cool to see these bounty sizes increasing so quickly. So you might be asking yourself now, how do I get involved? Well, call to action. Go to our site and sign up for an account. We have tons of bounty programs available right now. We're currently running a challenge where smart contract bug reports submit for Axelar Network, ZK Sync, Balancer, and Flamingo. All bugs that submit that are valid vulnerabilities get a 20% bonus for pwning. Reminder to please test your exploits in local forks. You should all be experts in forking mainnet after the talk from Darian. If you're new to the space and want to learn more or just don't know where to start, we have some great educational resources at our site on Immunefi/learn. You can also join our Discord to ask questions, keep up to date on the latest hacks, and participate in our community. And you can also follow Immunefi for constant updates on new bug bounty programs we launch, bounty payouts we make, and information on the latest security topics in the space. Yeah, that's our Twitter there. And that's it. That's it for me. Thank you guys very much. I hope you guys had a good conference.